So welcome to our continuing work on understanding unsupervised learning. We're going through two kind of stalwart algorithms, which are pretty fun today. We're going to finish out PCA, which is this old standby. We use it for dimensionality reduction, sometimes visualization. It's kind of a core canonical unsupervised algorithm. And we'll talk about that today. And I'll try and refresh and be a little bit complete there, because I know we got cut off kind of in the middle. If we have time, then we're going to go through ICA. We will have time for ICA. This is a fun problem. This is this cocktail problem. You'll implement it, actually. And it's one of the ones that's kind of a highlight every year. People talk about what are the favorite homework problems they did. And the reason we're going to go through it is it's a place where you make kind of a different assumption about how the noise works. It turns out if you make the kind of traditional Gaussian assumption here, which we've been making kind of through class, it breaks. And so it's just nice to have an exposure like there's more interesting things to do. And it's also kind of a fun problem. If we finish those two, and there's some chance we do, but if we ask lots of questions, that's actually even better. I'll show you some stuff about weak supervision, and I have some slides prepared for that, which are not in the main deck, but if we get to that, I'll post the slides. Weak supervision, the reason I would want to talk to you about it is it's a more modern technique. It's behind some products that you've actually used in the last while. And it's kind of one of these things that looks like an EM style model, but you can solve it in a very direct way. And since we're not having another exam in the course, you won't be responsible for it. It's a little bit more advanced. And so I can talk to you about kind of how that works without hopefully freaking you out. Okay, cool. So that's what I want to do today. So let's talk about PCA. All right, so PCA, if you recall, we were looking at these unstructured things. I'm just going to run through some of where we were last time. We're looking at this structure, and our structure is a subspace, and it's a non-probabilistic method. So the two things are, we wanted some structure that we were looking for underneath the covers. Remember, GMM and k-means, where there's a clustering kind of structure. Here we want to look for a linear subspace, and we wanted the non-probabilistic version of that. We looked at this kind of contrived example where we had pairs of highway and city miles per gallon, and we were plotting cars. And we kind of intuitively would guess, like, there are hybrids up here, there are SUVs down here, and trucks maybe, and economy cars in the middle. And we wanted to understand what is a notion of good miles per gallon that took into account both highway and city. And this was a way of motivating effectively that what we wanted to do was to kind of draw a line along the direction that explained most of the variance. That was our intuition. Most of the ways that they varied inside the data set, that was descriptive. So the way we did that is our first mathematical thing is that we centered the data. Recall, we took the data, we subtracted off the mean, and literally last time I just copy pasted this data and centered it at approximately the center of the data, which is mu. And we transformed it. And the reason we transformed it is we're using a linear mapping, that's what we want to do, and linear spaces go through the origin. So this just lets us use linear spaces and have one fewer degree of freedom when we map them. It's not important really to your conceptual understanding, although you should think about it, but it's really critical if you run these methods. If they're askew, there will be no line through the origin that potentially goes through your data. Once we did this, I want to remind you of some things that we're going to use from linear algebra. We had this idea around, we're going to prove formally what we mean by the direction of maximal variation. And we kind of thought that this line intuitively would be that variation. That is, when we projected things on the line, either we had them maximally spread out, that means we captured most of the variation, that's actually what that means, or we saw this dual thing in a second that the residuals, the amount of error in our prediction on that line was small, okay? And we'll talk about that again in a second. If you don't remember your linear algebra, remember that you can write, once you have an orthogonal basis, you can write any point in that space as in that orthogonal basis, namely every one of the vectors that are orthogonal, u1, u2 in this example, and their distances along those lines. And we're going to recall the math that does that, but that kind of gives you a new set of coordinates for your data. If your data were 1,000 dimensional, it was given to you in 1,000 dimensions, you could run PCA underneath it and find the direction of maximal variation, and maybe its second and third components. And then you could take that 1,000 dimensional coordinates, which are 1,000 numbers that you were given, and compress it down to 3. And that's what we mean by dimensionality reduction. What are the 3 best numbers, if you like, in some sense, that represent your data set? Okay? Now, just remember that fact that every point can be written in the basis. And really it's like the coordinates of like, how far do I go along u1, then I'm going to go along the u2 direction and get to x1. This is alpha 1 and this is alpha 2, okay, as we'll see below from last time. Now the convention is that U1 and U2 are unit vectors because we only care about their direction. We don't care about their length or their magnitude. And this is just what you do there. And so here U1 was kind of how good is the miles per gallon? And U2 was the difference between their highway and city miles per gallon, roughly. Those aren't formal statements. That's just to give you an intuition of what this basis looks like. So you can kind of have an intuitive feel of what you're doing. You want one direction, which is the principal component of variation. And if you had 1,000 different points, you would then look at the other data sets and say, what other direction is the second principal component, third principal component? And if you remember your linear algebra, that is just how you write down a basis. Okay, that's all I'm describing. But we have to order those bases in some way. We have to figure out which components do we pick first and among all of them. And that's what we're going to solve in PCA. All right. Okay, so this is all just saying x can be written in this form. And we may here compress from dimension 2 to dimension 1. What that would mean was we would probably just keep the number alpha 1. That would just be, we would treat x as its projection onto this line and just treat it as alpha u1. Okay? And that's what we mean by explains more variation. Okay, so we're going to find these directions today with some caveats, and we're going to think about thousands of dimensions to tens of dimensions. And this will be a dimensionality reduction because we're going to only keep those components. So before I move on, there's a lot of linear algebra in there. Ask me questions, and I'm super happy to unpack this because we're going to assume this information, as we tried last time, going forward. But I'm super happy to answer questions and derive whatever's here that's unclear. And if you have the question, almost certainly somebody else does. So please go ahead and ask. Please.
What if these alpha, which is basically the coefficients, are negative?
So they can be negative, right? So for example, in this direction, U1 is going this way. If you were to have a negative, it would mean that it was in the negative direction of that. These are signed, so they can certainly be negative. They're not positive scalars here. That's why we worry about their squares for how much of the residual is, because they can be positive or negative coefficients. Just like you can have something that first component is positive or negative, and the positive tells you to go this way, and then negative tells you to go that way.
So like we order these components based on the squares of the alphas.
We don't know yet, right? So what we're going to do is we're going to try and find, so all we know at this point that we're trying to make sure that we get there is that we can take an x and we can write it down in a basis. So x has its original thing that it's given to us in Rn, some large space. We can write it in new numbers, alpha i's for these ui's, and this is a different basis for the same underlying space. And then what we're going to try and do is say, how do we pick a good set of ui's to represent this? And what I'm trying to hint at is that we don't have to pick a complete space. We don't have to pick n orthogonal basis vectors. We're going to pick the top k in some sense. And that top k, is, we hope, captures the most variation. And we're going to make that precise in the next couple of write-ups. Awesome questions. Please, any others?
Just so that the top came, like you would tell us.
Yeah, we haven't gotten there.
Okay.
We haven't gotten there. Yeah. Wonderful point. Okay, so that's exactly what I mean. We're going to say, how do we find those directions? Okay? And last time we talked about this pre-processing. We're going to assume this for the rest of time. I would just say at some point reflect on this. We have to center the data. That's because we're going to look through lines that go through the origin. We want linear subspaces, so that makes sense that we would want our data to kind of have a chance for these lines to explain the maximal variation. That's why we center. That's important. We will also rescale the components so that they have about the same amount of space. So imagine if one of your components was miles per gallon and another one was feet per gallon. The feet per gallon, because it was 5,000 times, the numbers were 5,000 times larger, they would be at vastly different scales, right? And if you go through the calculations below, because you're taking squares and doing things, because they're at different scales, that kind of makes them unreasonably important, right? So one of the things that you'll typically do is then scale by the variance in each direction, and then allow them to kind of all be spread kind of about a Gaussian, because they're centered component-wise, and then divided by that variance. That's just the other piece of pre-processing that goes on. Okay. All right. So now we've done that. We've done those pieces. We need a couple of bits of mathematics just to remind yourself of what it means to find these kind of components. So here we have two components, U1 and U2, and they're unit vectors as we talked about before. And they're orthogonal. That means their dot product is equal to 0. They're perpendicular to one another. Okay. Now, what we want to find, one of the things that we have to find, or it's kind of a subroutine intellectually of what we have to do is to find the coordinate alpha 1 on this line, it makes sense that it's the closest point, actually, on this line to x, right? That would be the point that we would project it on. That's what projection means, actually. It's the closest point on the line in this sense, okay, in Euclidean geometry. So what is this line? This is the set of all t times u1, so that's any scalar, positive or negative, as pointed out, that scales this entire line. And so basically our optimization problem to find this component alpha 1 is to find the t that gets me to this closest point. Now geometrically, it will hopefully be intuitive that that should be perpendicular, right, to this line. This line here will be perpendicular, and the reason is the rest will be explained by u2. Okay? All right, so let's find out how we find the closest point to the plane, and I'm going to write it out now. So how do we do that? Just remind ourselves. So how do we do that? So alpha 1 is going to be equal to the argmin, this is just rewriting what I said, over all alpha, such that we have here x minus alpha u1 square. The square just makes our life a little bit easier kind of mathematically. Squares of norms are just easier to work with. It doesn't really make any difference in the underlying piece. But this is just saying among all the alphas, let me get that. Among all the alphas which are running up and down this line, I want the one that has the closest distance to x. That's what I'm calling the projection. Okay? So what does that equal? Well, this is the same as doing the argmin. Let me write it on the next line, actually. The argmin. And I'm just going to expand this norm out. So it's x squared plus alpha square u1 square minus 2 alpha x dot u1. Okay? And this is, I'm just writing the dot product in a notation, hopefully not too confusing. This is just the dot product. Okay? Just to make it clear without having little tiny dots to look at. All right. So a couple things right away. This term is 1 because it's a unit vector. It's a unit vector. And this term is irrelevant for alpha. Alpha's value here doesn't change the value of x. X is given. So this is equivalent for us when we take the derivative. Oops. When we take the derivative with respect to alpha of this expression, this expression looks like to us alpha square minus 2 alpha x u1. Okay? And when we take the derivative with respect to alpha of this thing, this is derivative with respect to alpha of this expression, that equals 2 times alpha, which is from the first one, minus x u1. Okay? Now, to set this equal to 0, this is equal to 0, this implies alpha equals x dotted into u1. Okay, comma. Okay? That's all that's saying. All right? So this is just saying something you may have forgotten from linear algebra or you're now remembering, which is that the dot product of a unit vector is actually a projection. Okay? All right. So far, so good? All right. Okay. Now, one piece here is that we can generalize to higher dimensions, to more components. And it's worth actually thinking about what this looks like, right? So the point is when we write this down, we're going to have here u1 to uk for some value of k. This is just for an exercise, for arbitrary value of k. Element of rd. Some x that's also living in rd. And then here, we're going to calculate coordinates alpha 1 to alpha d such that x minus sum k equals 1 to d, alpha k uk is smallest. Clear enough? This is finding the closest point in the subspace. Instead of a line, we're finding the closest point in the subspace. Hopefully clear and you remember this. If not, please ask a question. Super easy to explain. All right. So by the same basic reasoning, you compute the derivative, you unpack it. You have to use the fact that the UIKs are orthogonal. Why? When you expand the squares, right, you're going to get products of uk dot into uj, and those will cancel out. And so you'll basically have just a bunch of expressions that are present in which alpha k is going to be x minus uk. And this is only because they're orthogonal. Only because orthogonal. uk are orthogonal. Okay? And you can do that derivative very, very, very quickly. Okay, now this quantity here is important. Well, that's a terrible highlight. Let's use this one. This thing here is called the residual. All right. All right. This is the residual. And what we care about when we're going to do PCA is we either want to find a set of points, a set of directions, such that when we do this projection onto them, the sum of all the residuals is minimized. Okay? So this tells us the residual for a given point in a given basis. And now I have an optimization problem, right? And I'll write it out formally in a second, but intuitively you can think about what's going to happen is I'm going to pick k of these u's that are going to be orthogonal. There are many of them that I could pick, many orthogonal bases that I could pick. I pick one of them. Then I project all of my data onto that set. I measure how well I did by either how much I captured in the data set or by how much was missing, which is the residual. And this is the residual. I then have that per point, so I sum up over all of those. And this gives me a score of how good that basis was. And among all the bases, I want to pick the one that minimizes the residual or maximizes the projected subspace. So let me write some of that down, and then you ask questions if you like. So we can find PCA by two things. By the way, this seems like trivial, potentially, that the maximizing the projected space or variance and the minimizing distance are the same. It's actually not true in general for other geometries. So it's actually quite a nice thing about Euclidean space. That doesn't matter to you, but just kind of a comment. Minimize residual. All right, so let's do this one. This is the one we're going to do in class. Maximize the projected space. So let's do it for one vector. So now we want to pick among all the possible u's. What's the version, what's the particular setting of u that explains the most about our data? And so what that's going to be from our previous discussion is this. Max u over rd subject to u equals 1. This 2 norm is equal to 1. Over an average over all the points, although of course such a constant doesn't really matter because we're maximizing, but it's nice to have the right scale. u dot xi square. Okay? So what we're saying here, we pick a direction, and this direction we want to get the largest dot product, right? How much, this is x1 projected into this is the alphas. The sum of those alpha squared i's, we want to be as big as possible. So we want to pick the direction among all the directions. So imagine in 2D, you're just kind of spinning around, and you're judging how great the subspace is by maximizing how much is present. Okay, we need a couple facts to solve this. Hopefully the point is clear. We need some facts to solve this. Okay. So first fact we need to recall is let A be a symmetric and square matrix. Which kind of makes sense. Okay? Then, it's a normal matrix. And in particular, it can be written like this. U lambda U transpose, where UUT equals I, the basis is orthogonal, and lambda is diagonal. Okay? Not all matrices are diagonal. Not all matrices are orthogonally diagonal. But if it's symmetric and square, it's called normal. then it has this. And lambda has a nice interpretation. Lambda I, since it's a diagonal matrix, equals lambda I, and we call these the eigenvalues. Lambda 1, and they're real. Okay? By convention. So we order them this way, just because it's nice to talk about them as lambda 1 being the big one, lambda n being the small one. Okay? Now, if you don't remember your linear algebra, maybe this doesn't seem mysterious to you, but if you think about the underlying model, there's no reason in general that these things should even be real valued. They could be complex valued in general. But if they're symmetric and it's nice, then this happens. They're real and you can order them, which is really nice. Okay, so we're going to use that fact. And if that's confusing to you to remember what happens when you diagonalize over the complex plane, don't worry about it at all. Just take this as a fact. Okay? All right. So these characters here, as I mentioned, these are the eigenvalues. All right. So recall, if x equals sum k equals 1 to n, alpha k uk, where u1 un equals u, we can write the following thing. We can write alpha x, ax, is equal to u lambda u transpose x. This is equal to u lambda sum k equals 1 to n, alpha k ek, let me write it like this. I don't want to write it that way. Yeah, okay, perfect, yeah. Alpha k ek, what's gone on here? U transpose u is exactly the identity. So all that's going on here is, since it's when I dot product uk into one of these, which one survives? Exactly uk, right? If it's different, if it's uj that's different, then they're going to contribute 0. So this becomes alpha k in the standard basis. This is the standard basis. If that's confusing, ask a question. What's going on here again? X is written in this form. What happens when I multiply u transpose by x? It multiplies it by each of the ui's. Only one of them survives. For the kth term, only the kth one survives, because otherwise they would be 0. And so I get this. Then when I multiply it by the diagonal matrix, I get u times sum k equals 1 to n, lambda k alpha k ek. And then I get back to sum k equals 1 to n. I multiply by u again. I get lambda k alpha k uk. Because again, when I multiply ek, the basis vector, right? This is the vector where it only has a 1 in the kth position. By u, it selects out uk, and I get back. And so what this means is, this is a long-winded way of saying if I multiply a in this basis, all it does is act by multiplying by the eigenvectors. This is an eigendecomposition, if you remember it. That's all that's going on. Okay. All right? Please.
How do we control over here? How do we generate a case so that we get all of these nice properties that we can get all of the use? Because once we have the use, then you can use the residual minimizing formula that we get.
Yeah. So I think we haven't gotten back to PCA yet. We need one more fact. Hold on just 1 minute, and we'll come back to that. We're just recalling facts from your linear algebra class. But it's a great point. You should be thinking exactly that. All right. So let me just point out one fact here, which is that if I take the max over all the unit vectors of x transpose x, A, it can also be written, and this is the formula we've been kind of hinting at, as alpha square sum k equals 1 to n, alpha k square lambda k. Okay? So now, if you think about this, how do you find the principal eigenvalue? How do you find the largest way to express this? Well, since we only get to spend our alpha squared along the components, and we only have one unit to spend, what maximizes this expression? Well, we want to put as much value. Oh, go ahead.
Alpha squared.
Because when we multiply here by x, alpha times x is going to be equal to this expression. And then when we dot x in again, we get the alpha squares because they pair up to one another. Yeah, apologies if I went too fast. Great question. So we have the alpha squares times the lambda k's. Now the lambda k's, because they're, let's imagine they're 1 to 10, where would you put all your mass if you wanted to maximize this? Well, on the largest one, right? So how do you maximize the amount of mass you put on the largest one? You put, in our notation, alpha 1 equals 1. Because the rest are all then equal to 0, this is going to be the largest one, and that's the principal eigenvector. Imagine they're strictly different. Does that make sense? Please.
Could you go over this hard line, like when you multiply u with that summation, any x, yeah.
Where, here?
What again? Yeah, to the right, yeah.
This thing?
Yeah. So how does it then suddenly become, for instance,
This one is just the fact that it's diagonal. So ek times a diagonal is just the kth unit vector times that value, and so that pulls out lambda k, which is on the diagonal.
And then we just convert it to a summation form.
Yeah, and then when you have a unit vector multiplied by a matrix, it just selects out that column. Yeah. Awesome. Okay, but is this clear? If I want to maximize this, I set alpha 1 equal 1. Right? Because we know lambda 1. Now, what if lambda 1 equals lambda 2? That is, there are two eigenvalues that are present. Lambda 1 equals lambda 2. Then it turns out there's an entire subspace of solutions, right? I could pick any alpha 1 and alpha 2 such that their squares sum to 1 anywhere on that circle. And if lambda 1 equal lambda 2 equal lambda 3, now I can pick anywhere in a subspace of size 3. That's going to be important when we think about how well-defined PCA is, because it's only well-defined what the principal component of variation is if lambda 1 is strictly bigger than lambda 2. Right? If there's no gap, then the coordinates aren't well-defined anymore. I can pick anything I just described. Does that make sense? All right, please.
Why is alpha equal to 1?
So alpha 1 is equal to 1. And the reason is, so if this constraint, this norm constraint, means that I have to pick among all the alpha such that their squares sum to 1. So if among all the ones that squares sum to 1, which one's going to give me the biggest value? Intuitively, I want to put all my mass on lambda 1, because lambda 1 is the biggest value, right? And so that setting, I would set alpha 1 equal to 1 and all the alpha k equal to 0 for k greater than 1. That would be the value that I would pick there. Because that one's guaranteed. I can't really do better than that. If I slide off even an epsilon amount of mass, well then it's going to a smaller eigenvalue, and because I lost that mass, I would get epsilon squared times that. Okay? You could also just compute the derivative using Lagrangian if the intuitive thing doesn't make sense, which we did 2 lectures ago. Cool. All right. So let's go back to PCA and say exactly where do we get this UI. The thing I wanted to point out that is here, I'm going to come back to this point about what happens with lambda 1 and lambda 2. If you missed it, don't worry. I just care that you're aware that what we're doing in the maximization. Now back to PCA. Okay, so recall, I'll just go up here. Sorry, I'll copy because I'm extremely lazy. Where was our PCA? Ooh, where did we do this? Oh, here. I just want to make sure you realize I'm not doing something strange and changing the expression. This is what we wanted to deal with. Well, this expression here, we can rewrite. And we can rewrite it as xi transpose u transpose, x transpose u transpose xi. Sum I goes from 1 to n, 1 to n. Okay, let me drag that and give myself a little bit more space here so it's not crowding you too much. Okay? So this is equal, these two expressions are equal. I'm just expanding out the square. But this is pretty nice because now I can pull out u. Oh, sorry, I wrote it backwards. I didn't want to do this. Let me write it the other way. That'll just make my life easier in the next move. U2, I'm so sorry about that. Expose, transpose, u. Okay? Sorry, that was foolish. It's true, but foolish. Okay, so now I can pull out the u's because they're on the outside. This is u transpose sum I equals 1 to n xi transpose u. Okay, why is that? Because this is linear. So I can pull this out of the sum. And all of these things are paired up. This thing here is a quantity that you may remember previously. This is the covariance of your data. Why is it the covariance? Because you subtracted off the mean. This is the sample covariance. And so here, I can push the 1 by n inside. Let me do that too. 1 by n. And then it's really the sample covariance. Okay, this thing here. So then what will u be if I want to maximize this u? Well, it will be the principal eigenvalue, right? This is an eigenvalue problem. Just as we went up here, it's now of this form. We can verify, is it symmetric? Yeah, it's a symmetric, it's a sum of, each are a sum of symmetric matrices. So the covariance is symmetric. It is actually really a covariance matrix. It also happens to be positive semi-definite. That means all the lambdas are non-negative. So that's good news. We didn't need that, but that's nice to have. And now when we look at the u's, as we go through there, we have to pick a direction. Which direction do we pick? Well, we're going to pick the direction that corresponds to alpha 1, which is u1, right? Which is the basis. When we do the decomposition here, it's the principal eigenvector of this thing. So the best u to pick is the principal eigenvector of the covariance. Right? Some of you are nodding. Some of you look like I said something horrible. So please, both ask questions.
Is this the A matrix that I was asking about?
Yeah, this is a covariance. We're going to sub this covariance matrix into the A. Yeah. Awesome. What happens if we want two components? What do you think we pick? Anyone? The first two that correspond to the largest two eigenvectors. 3, the largest 3. If the first two are equal and you want one direction, lambda 1 equals lambda 2, now you got a problem because you have two potential representations for it. But you can still pick a component of principal variation. And that's the way that PCA is potentially undefined. Okay. All right. Cool. That's all it is. So how do we represent data with this, just to make sure it's clear? Well, we map xi to some, let's say we picked d dimensions, xi minus uj. Namely, this is its coordinates in the top k eigenvalues that we picked. On average, this captures the most variance in our data. And we just keep, this is a scalar. This is what we were calling alpha j earlier. We just keep these k scalars. Okay, so this map, what it does, it takes in 1,000 dimensions. Let's say I started with 1,000 dimensions. Then it's going to pick 5. Which 5? Well, they're going to be a blend of those. They're not going to be any individual dimension. They're going to be these eigenvectors of the underlying covariance. They capture the most. The reason we like them is they capture the most of our data. They throw away the least amount of our data, which is the other residual interpretation. And this gives us a map that goes from R, let's call it big D, down to R little d. Okay? And that's in what sense this is a dimensionality reduction. And we can use that, for example, to take our data and take it from 100 dimensions and project it onto 2 and visualize it and draw it on a map. Yeah, awesome. Please.
Before we get around, so I guess we need to have an estimate of what the small d will be.
Yeah, great question. So you want to know, how do you pick k or d here, little d? So let's, here, in contrast, for the last 3 lectures, I've been telling you I have no idea how to pick k. Here I at least have an idea. Oh, go ahead.
Oh, I'm just confused. It seems like we just mapped everything into a new subspace that is...
I think I confused you with something. So let me make sure. This, let me just call this k, just for now to make this. K is less than what you're thinking of as d. How about that?
Yeah.
Yeah.
So basically we map everything into a subspace, but this subspace is still d-dimensional because of the length of the vector v is in.
No, that's a great point. So it's decomposed into d-dimensional vectors, but it only now takes k coordinates to represent it. So again, going back to the two-dimensional picture, we have a two-dimensional picture, but we projected everything onto the line. And so now we can represent things by just its distance on the line, the alpha 1. So we've taken two scalars, which were like its x and y coordinates, and reduced it to just one, which is the alpha 1. Does that make sense? Awesome. All right, so let's see how we pick k here. How do we pick k? And this won't be super satisfying, but you know, whatever, be fine. Okay, so this actually does have some kind of trick. So what does this actually mean? So this is basically looking at the trace of A, which is equal to this sum on the bottom, lambda I. Okay, so if you remember your linear algebra. But basically what it's saying is, what I want to know is how much of the space am I explaining? So imagine I have 100 dimensions. Intuitively, if I get the top 10 of them, the worst case is that they explain 0.1 of my space, meaning that my sum of those eigenvalues are about 0.1 and I'm throwing away roughly 90% of my data. It's not what it means, but just kind of think intuitively. What this is saying is that traditionally people will pick k here so that they explain a lot of their data. And so if does your data, like, you know, as a rough guide, if I pick 10 components of your data and do PCA on it, do I capture 90%, 95%? Then that means that was a good selection. And you can now compare k's based on how their eigenvalues are ordered. If it goes down to 10 to the minus 10, right, your fifth component is 10 to the minus 10, you don't need it. Pick the fourth instead. Just pick basis of 4. So now it gives you a way to actually start to compare them. And you can get error guarantees. You may worry computing these eigenvalues is super expensive because you have to compute like an SVD on some mega matrix. But you don't have to, and the reason is this is a trace. And if you remember your trace equalities, you can just sum the values on the diagonal to get the trace, which is the sum of the eigenvalues. Please.
So if you pick a k that was like too large, and say that this quotient came out to be like very, very high, like 0.999.
Right.
Would you say that you're overfitting the data?
Yeah, it's exactly right. It's a thing you're overfitting. You don't need to do it. And so it's kind of like if you're keeping those extra pieces of information, like intuitively you want the smallest k that you have most of your data. So you can tack on more, but it's kind of like what's the additional value to do it? Traditionally you'll use k, as I said, PCA kind of as a visualization technique or like to get some rough sense of the data. And so you try not to have k higher than 2 or 3, and it just provides a sanity check. Like if you run PCA and the first two components of your eigenvalues account for almost nothing in your data, then it's not really clear what conclusions you can draw, right? The other place where it can cause you pain is the thing that I keep illustrating, which is that if lambda 1 and lambda 2 are equal to each other, which on real data is actually very unlikely, but numerical issues could make them kind of come together, then the coordinates could be pretty fragile, right? So I run PCA once and I get 1, 2, 3 as my, alpha 1, alpha 2, alpha 3. But then I run it the next time, and because I chopped it 3 and the first 4 were equal, some new coefficient comes in, right? So really, like, those are the instabilities that you worry about the most. If like your lambdas or a bunch of lambdas are really, really close to each other, then your coordinates aren't really preserved and anything inside the subspace goes. So that's the other problem with PCA. It really only makes sense when the spectrum is separated. And people don't usually check that, and as a result, they lead to erroneous conclusions. So you tack on too many, you get there, and then also you can have these issues about non-fidelity in the representation. Those are the two main ones. You got it perfectly. Okay, awesome. Any other questions about PCA? Now you know it. You love it so much. All right, great. All right, let's talk about ICA. All right, so ICA sounds very similar to PCA. We only changed one letter, but it has nothing to do with it. One has nothing to do with the other. So that's refreshing. But they have something about them that I really like. So, all right. So first I'm going to tell you the high-level story of ICA, which is this cocktail party story. High-level story. Then some key facts. These key facts are useful because you will run into them in your homework, and I just want to highlight them. And then we'll talk about the model. And the model will be the least interesting part. So here's how it works. Here's the high-level story. We have people, and by the way, I think their homework is the world's most boring cocktail party. I think they like count numbers to 10 or something. So it's not like you're going to hear some salacious gossip. You're just going to hear people counting to 10. Some TA from like 5 years ago. All right? So anyway, so you have people. Here are the two people. They're happy. Those are our people 1 and 2. We have microphones over here. Mic 1, mic 2. Okay? Now here's our problem. When the people speak, they don't speak directly into one microphone. They're just ambient microphones. And so what happens when this person, compresses the sound waves is that, boom, it hits microphone 1, but also it hits microphone 2. Similarly, when person 2 speaks, they speak in some way. This is supposed to be the same wave, by the way. So like the wave didn't change based on them, but it just took longer to get to the microphone. We're not going to worry about length too much. But the point is, what microphone 1 and microphone 2 see is a mixture of the sounds. They don't just hear one person, they hear 2 speakers simultaneously superimposed on one another. And the goal is to take what we record at these microphones and recover kind of the time series of what they actually said. And since if we had the wave, that's just the air, we could play it through a speaker and we would actually hear what person 1 and person 2 said. And you'll be able to do this. And it works, which is kind of wild. Now, I do want to emphasize, having built things that look sort of like this is a naive way to look at the problem in the sense of like what you would build if you were doing this in industry, but so what? It gets you the core principles. And you can look, there's whole things about speaker identification. And in fact, like there are certain companies that when they ship their products, they brag about how they can identify different speakers in the home. So like as weird as this is, like people ship products based on their ability to do this. Okay? All right. Please ask questions if the setup doesn't make sense. 2, we have data X. And we'll see it for some time. We're not going to assume things or make this simple. The people aren't moving around in the room. They're not changing, just to make our lives a little easier. Okay, so we need to look at what does the actual data look like. All right? So as I mentioned, speaker 1 is going to be kind of this time series that looks like this. Okay? Now, we don't actually see the whole continuous thing. What we see is we see speaker 1. We don't even see this, by the way. This is kind of, we get samples at various regular intervals. That's the way we conceptualize the problem. And this is like how audio processing works, right? 2 at time 1, and so on. Let me just draw this and then I'll talk. Okay, and these should be evenly spaced if I could draw properly and had enough patience. Okay? Time 1. The point is what you see is that you just get these measures of intensity. So STJ is speaker J intensity at time T. Okay? Now we want to recover this. If we had this, we're in good shape, right? If you think about how you actually record audio, kind of high-end audio is usually recorded around 44 kilohertz, right? Give or take. You can probably understand people much lower kilohertz. I don't know exactly where it breaks down. But my point is like, this is actually how digital recording works, right? You sample at a bunch of points, you get the intensities, and then you play it back through a speaker. Okay? All right. And then there's speaker 2, which I'll also draw. Oops. And then, just so it's clear, like we sample them at a bunch of points too. Maybe speaker 2, more loquacious, I don't know. S1, 2. Oops, those look terrible. I don't know why I'm gonna fix this, but I am. And these are sampled at the same time points. So my drawing is imperfect in many, many ways. 2, 2, S, T, 2, so on, blah, blah, blah. Okay? And these are going to be sampled at the same time points just to make our lives easier. Okay? All right. So now, we don't get to see this, as I mentioned. We don't see S1 and S2's time series. Right? We get to see the microphones. Only XT1 and XT2, which are sampled at the microphones. Okay? So far, so good? So we need a model of how we're going to do this. And of course, kind of our model from what we described above is going to look something like this. What we observe at microphone J at time t is a mixture of something from speaker 1 and something from speaker 2. Okay? So microphone J, just to make sure it's clear here, mic J sees a mixture. And we're going to assume this mixture is fixed, right? Just for the moment, right? If they're moving around the room, that's not true any longer. But we're going to assume it's fixed for the moment. Okay? So I can write this compactly as x of t equals a of s of t. All right? Now, what do we know here? This we observe. This is the data. Both of these are latent. We don't know the mixture. We don't know the speaker intensities. Okay? For the moment, I'm going to assume that the number of speakers and the number of microphones are the same. You can imagine, because there's a matrix here, that if I have only one microphone, this is going to be substantially harder, actually impossible, to do the reconstruction. But I'm going to take advantage of the fact that I have different mixtures at these microphones. Okay? So assume I have number of microphones the same as the number of speakers. Okay? So is the setup, the high-level story and setup clear? Intuitively, what should happen? All right. Let me write some math. Sure. A is actually the mixture. So A right here, this model says that what we see at time t, at microphone J, is some fixed mixture of what speaker 1 said at time t and speaker 2 said at time t. We're not modeling any delay or anything like that. So they make the sound, they go ah, and then it hits the microphone, and then the mixture of person 1 and person 2's pressure hits the microphone at the same time. They don't actually matter for now. The physical units don't matter in any way. But you can think about them as any unit of pressure that you want. Okay. A is unitless. A is just a pure mixture. You can multiply and add things because the S's are the same type. Yeah, cool. All right. So let's make this a little bit more mathematically precise. So we're given x1, xn, element of R, D, and D is the number of mics and speakers. What we have to do is find S1 to Sn that's also amount of RD. Okay? So I'm preferring to have the notation over time. We also are going to find, although we really don't need it for the model, this A that is d by d, okay? Such that x of t equals a s of t. Now, if we estimated A, right, there's a pretty easy way to find what we wanted. If we knew A, someone gave it to us, this problem's trivial. Just take the x's, multiply by A inverse, and you have yourself the s's, right? Now, the terminology is we call A the mixing matrix for the reasons I just outlined. A, the mixing matrix. And W equals A inverse, which we'll use the unmixing matrix. So why would I introduce and bother you with this? It turns out that W is actually the right way to write a lot of the guarantees, and you'll see why in a second. Okay? So we're going to write this as, right, W is equal to W1 transpose to WD transpose. And I'm just doing this so that I can write the following. So that, this is just one way of writing the inverse, so that SJT equals WJ times XT. Nothing happened here. I'm just giving you notation of how I think about the mixing, and then this inverse is going to be important. The inverse is kind of obviously important because we want it, if we had the A, we would multiply by its inverse on both sides, and that would tell us the speaker that we were after, right? So W is what we need to multiply by. Okay. Now the things that I actually find interesting about this model. So some caveats, we talked about some of these. A does not vary with time. We're assuming that. Time. If it did, we have to use something more complicated. So we're not going to do that. 2, this is more interesting to me. There is inherent ambiguity in this model. I like when there's inherent ambiguity, when you can't tell two things apart, because it forces you to understand what the model is doing. So one thing, we can't determine speaker 1 versus speaker 2. We have no idea who's speaker 1 and who's speaker 2 in real life, so we can only determine up to kind of how we permute their time series. Okay? So speaker ID is opaque to us. Maybe one time we run the algorithm, are indistinguishable. We don't know the labels. Okay? Of course, we can tell that there's one person who's saying numbers in English and one who's saying numbers in French. We just can't tell who's doing what in this model. The other thing, which is maybe a little bit more subtle, is we can't determine absolute intensity. And I'll just write the equation. And it's because we're multiplying two things together. So notice that if I take any constant and multiply it times A, and then take that same constant and multiply it times S, this is still equal to A of S of t. So we can possibly only know that the person, we can't tell how loud S1 and S2 are. We can tell relatively how loud they are. But the mixing matrix we could multiply by a constant, and it wouldn't change anything, right? The scaling would go through. And because we're multiplying them in our framework, we can't determine this either. Now that has a surprising thing. And this is why I like to teach it intellectually. Oops, surprising. The speakers cannot be drawn from a Gaussian distribution. We're going to have to make some statistical assumption, but they cannot be Gaussian. Why? Suppose they were. Xi would then be a normal drawn with some mean from AAT. But then as we saw before, if UTU equals I, then AU generates the same data. What does that mean? It means that any rotation of A generates the same data multiplied by U. And the reason it happens is because the data here are rotationally invariant, because their covariance matrix is A times A transpose. And that is not sensitive enough to tell about all these rotations. The same reason we loved Gaussians, because they were rotationally invariant, means that symmetry, we can't recover anything in this problem. And so at that point, you may think, gosh, there's no way we're going to be able to do this. We have all these symmetries around the speaker, and we can rotate the the intensities in any way we want. What are we going to be able to do? And it turns out you can recover something here. And weirdly enough, as long as the distribution, roughly speaking, is not Gaussian and is not rotationally invariant, you can recover it. And that's kind of remarkable, and it's worth thinking about. Okay? Now the algorithm is going to be so trivial. The algorithm is just going to be gradient descent and MLE. We're just going to set up a likelihood function and run everything that we've been running so far. Okay? That's it. All right. Now, we need one trick, 1/2 second, 2-minute detour, because this causes problems every time people look at this. It's just one little detour about how random variables behave under linear transformations. Under linear transform. All right? All right, and this is just, the reason I'm doing this is it's a key confusion. If you remember I don't know, I'm not going to say what you should remember, some calculus thing. Just basic, change of variable formulas for integrals, this will make sense, but we can draw it in pictures and you don't need to know that at all. So here we go. So just imagine I have something that's uniform on 0, 1. Okay? And now I have a new variable, u, which is equal to 2 times s. What is the PDF of u in terms of s? Now we're tempted to write P of u x over 2 equals P of s of x. Okay. Now, let's take a look at the PDFs. So here's the PDF of u. It goes from 0 to 1, and what's its height? Well, we integrate over the entire thing, it's 1, right? This is our PDF of u. Sorry, of s, sorry, PDF of s. S. This is the uniform. Now, for u, what happens? We go from 0, here's 1, to 2. We know we have support from 0 to 2 because it's a uniform distribution, right? You grab a point here, you multiply it by 2, and it's going to sit somewhere in here. Oops, go away. Right? It's going to sit somewhere in here. But what is its height? It's got to be 1/2. So this relationship is clear. So PS of x is going to be equal to 1 if x element of 0, 1. It's 0 otherwise. Pu of x is going to be equal to PS of x over 2 times 1/2. Okay? And that's just the normalizing constant. And so this key issue here is this normalizing constant. Normalizing constant. That's it. So when we do this in higher dimensions, we have Pu of x, and we want to map by some linear a. Oops. So that is like AU, for example, right? What happens, right? Right? Oh, sorry, AS, that's the way we're writing this, because I want to keep the notation. AS equals U. What happens in higher dimensions? Well, we still have Pu of x is equal to PS of A inverse x, but we need a normalizing constant here. And how does it take, if you imagine I'm taking a box and I multiply it by A, a matrix A, how does the volume change? That's the determinant. That's all a determinant does. It takes a box, and the volume of it is going to be exactly proportional to the absolute value of the determinant. The determinant is signed because it's an oriented measure, but that's what you get. Okay? You can convince yourself in 2 dimensions pretty easily. In higher dimensions, it actually requires a little bit of work potentially to do it. And this you probably learned as your change of volume integrals formula at some point, times the determinant of W. Okay? Okay. Now the thing that I used here was the fact that 1 over the determinant of A is equal to the determinant of A inverse when I did that. Okay? So the point is when you do change of variables, you have to take this determinant into account. You probably did this with a Jacobian at some point in your life. And if you didn't, don't worry about it. It's not that big a deal. It just says, if I take a box and I map it by a linear transformation, what's the volume of the box? Going back to this uniform case. And then if you care about how you would probably prove this, you just think about like integrals, you break it into tiny little boxes. That's it. Whatever space you're integrating. So this, we did it for 1 box, but you can do it for many. Okay, so we're going to use this formula for the rest of our time. Please.
For the earlier part, we wrote PUX over 2 is equal to PSX, PSX. And how does this actually relate to U equals 2S? Because like, we're using U as a parameter.
Okay, so yeah, so the idea here is that we have a probability distribution in one space. Now I want a probability distribution in my new space. So I have from 0 to 2. So I'm going to take the x and I'm going to divide it by 2, and whatever the height is over there, I'm going to get it. So if the height is 1, I get it. If the height is 0, then that should be right as well. But when I do that, the problem is the probability distribution I had, I'm using that value, will be 1, right, when I do that. And I need to just multiply by some constant. So I'm thinking here about the PDF for that random variable.
Yeah, so basically U and S here is a parameter or a random variable.
It's a random variable. And so a random variable is nothing more than like some function on the, it's just an integral.
Okay.
Yeah. Awesome question. All right, so once we have this fact, this problem is super easy. ICA is MLE. Why is that? P of S equals sum j equals 1 to d, PS of Sj, okay? This is where we use the sources are independent. We have to assume this in the model. And they have some distribution that's not Gaussian, but not Gaussian. This equals, so then P of x is now equal to the probability j goes from 1 to d of PS w times x times the determinant of w. But now this is something that we can compute. This is written in terms of x and our matrix A, and we can just do gradient descent on it. Okay? So how does that work? Here's the key technical bit. Right? We're going to set PS of x proportional to g prime x for g of x equal to 1 plus e to the minus x inverse. There's nothing really magical about this function except for it's not rotationally invariant. And then we can solve the likelihood of w is sum from time goes from 1 to n, sum j goes from 1 to d, log g plus wj xt plus log determinant of w. Okay, so maybe this looks pretty intimidating, but what happened here? This g is just some likelihood function. I don't actually care what it is. That's the thing that's weird. That's the thing I want you to confront. It's not that it's like some specially chosen function. When we would pick the Gaussians, we were picking it because of computational and kind of other reasons. Oh, it only had 2 moments and we could compute everything we wanted. This is basically saying, honestly, I can pick almost any g I want, any likelihood function I want on the speakers, as long as it's not rotationally, as long as the measure isn't rotationally invariant, there will be a unique solution if I look at enough data. That's kind of fun. That's kind of an interesting thing to think about. Then you say, what g do I pick? Well, I'm going to pick this one because I know it's not rotationally invariant. People pick other ones. How do you pick a measure? Well, you pick the PDF proportional to something that looks like a CDF. What does this function look like? It's just a sigmoid function. So I pick the probability distribution, so it's kind of low to high. It's not rotationally invariant on each component, and I'm done. And that's kind of wild, okay? I'm not super worried that like you grok absolutely everything here. Again, these lectures are not supposed to walk you through line by line and read the book to you. What it's supposed to do is give you a high-level structure for how this algorithm is going to go and what are the key twists. Now, the one thing that'll probably scary to you is you're like, well, I don't know how to compute the gradient of the log of a determinant. And weirdly enough, that actually has a form. So that is actually that's an object that you can compute and compute gradient descent on. And so you just run gradient descent on W. You have to do some derivatives in the old days. I guess now you don't have to compute derivatives anymore. You have autodiff software for you, which will kind of do it automatically. Like PyTorch will do this for you, or JAX or something. But maybe we make you do it by hand. I don't know if we actually do that. But if we do, you can do it. It's not bad. You look it up, or you derive it. It's not super hard. But it is weird that it works. Okay? And miraculously, I'm not going to have to convince you of this in class. You run the thing, and you will hear someone saying 1, 2, 3, 4, 5, some TA. And it will work, even though what's at the microphones is a mix. It's pretty wild. Okay? All right. All good. Oh, by the way, so what is the log of the absolute value of the determinant? Right? The determinant is the product of all the eigenvalues, right? So if you take their absolute value and take their log, it's going to be the absolute values of the sums of the eigenvalues. Now that looks a little trace-like, so you can imagine why this is actually relatively easy to compute. But your W is small. You can brute force it for these kind of things. Okay, awesome. Any questions about this? Please.
And can you just repeat what is the piece?
Awesome. Yeah, let's
Yeah.
this piece right here. Yeah, so what we're doing is we have P of the speakers, each one of them, some probability distribution. I'm being vague at this point when I was writing it because I wanted to basically get to the point, we can use any distribution. That's the weird thing. Basically any distribution, so long as it's not rotationally invariant. So I don't know what PS is yet, but just imagine it. Now I'm going to move it to a distribution from Sj to a distribution on x's. So the speakers I can't observe. I don't get to measure them, but I do get to measure the x's. Now I only have one variable that controls everything. That's W. Now I can do gradient descent on W. I didn't know how to do it on their product before, of setting S and W as a product, but because there's only one now, I can run gradient descent on it. And it happens to be kind of nicely concave and all the rest of the stuff I want.
So you're going from one distribution to another using this variable called W and then using gradient descent.
Exactly right. And the thing that's weird here that I want you to confront is, and when you do the assignment is like, if you use the standard distributions, you don't get a unique answer. And weirdly enough, almost any distribution you use will work. We happen to pick this one, but you could have picked something else. And that's kind of wild. So, right? That's a weird thing. It just has to be able to distinguish it. And what you think about there is the prior on the speaker doesn't matter too much. They just can't mix in some awkward way. You can't rotate the speaker intensities and have it make sense. You have to be able to distinguish kind of up versus down. Fantastic. Other questions? All right. So I'm going to spend, please.
Yeah, about this G, yeah, like how exactly you get, like how do you get the G of X? This one is directly proportional to.
Yeah, you don't, okay, so I can take any function I want and normalize it, as long as it has like some variance, it's smooth and other things, and normalize it from like -1 to 1 or -infinity to infinity, as long as it's integrable, and make it into a probability distribution, as long as it's positive, right? Positive, this function's positive. I want it to go kind of, I want it to go from low to high, so it has that nice feature to it, and I don't care about anything else. But now that's a CDF, right? Because now I have a function which the integral of which is 0 to 1, and then what I'm going to do is I'm going to take a differential, and that's what gives me the PDF. This is just probability theory stuff. But yeah, and you're like, the thing that should bother you and is bothering you is like, why did you pick this function? And then I'm telling you that's disturbing. Go pick other functions, it still works. But there's one function that if we use, which we've been using the whole quarter, all of a sudden everything breaks. That's weird. It just means that like, not every prior matters. Sometimes priors get these like, undefinability things, and it's coming from this rotational invariance. And that's weird, it's gonna bother you, but then you run the code and you're like, oh my God, it works. Then you can play with it, see how close you can make it to rotationally invariant, if you motivate, or you just do the homework and turn it in out, either way. But that's what's interesting. Cool. All right, I'm gonna use our last little bit of time together to tell you something kind of different, which was sometimes about weak supervision. This will be less mathematical and potentially have more bizarre pictures. We didn't get any activity on the thread. I want to tell you about one trend, since this is our last lecture together. Tengyu will take over. And we'll see if we get through this. All right. Okay. So I want to tell you about weak supervision, and I want to just motivate it for you in the last 20 minutes and why we care about it. And mathematically, the reason we care about it is it's an example, the underlying model that I'll show you is an example of these EM style models, but we can solve it exactly in a lot of situations. These are my slides, and I have to give these keynote, I had to give a keynote this morning, I have to give 2 more this week on random conferences. They have lots of weird pictures on them, just ignore them, okay? So let me motivate for you why I care about weak supervision, and then I'm going to skip over some stuff, and then we'll try and get to the mathematics of the model, okay? So the reason we started thinking about weak supervision, and others too, and this thing we call data-centric AI, was that machine learning, at least in the supervised setting, has 3 pieces. It has a model, which you're learning a lot about in this course. It has training data, which we've talked about a whole bunch, and it has hardware. And the thing is, which is weird outside this class, and for a variety of good reasons, models have become commodities. So all of you in this room can go download, Google, Microsoft, Stanford's latest models. Just the culture of AI is that we put everything online. And there's been a ton of investment in that. So if you want a state-of-the-art natural language model, you can download it. Like go to Hugging Face, download it. You want a state-of-the-art vision model, there's a tutorial somewhere that will allow you to do it. And you can get it instantaneously. And because of the cloud, hardware is a big problem. It's not a big problem, people can get access to it. Okay? Still an interesting problem, but it's there. But training data is hard. This was the original idea. And the reason training data is hard is it's the way that you encode your problem about the world. It's how you label it. Now, when I tell you about supervised machine learning, the first day we have X and Y pairs, and I never tell you where they come from. You have X and Y pairs, they came from God herself, they landed there, and you're like, well, this is where machine learning starts. But that's not at all how anything works in machine learning. It doesn't start then, and it's not like hanging out with Beyonce, it's like living in a sewer. So if you want to do this stuff in industry, it is much more like hanging out in a dirty, filthy sewer. You have all these data streams, you don't know where the heck they came from. They all have weird errors, they all have weird correlations with one another, and it's a huge mess. And so we started to look at this problem a couple years ago with many other folks in the field, and we just wanted to put mathematical and system structure around how to make this less awful. Okay, that was the motivation, right? Now I'm not going to bore you with the fact that like people actually do this and all the rest. It turns out that this is an interesting area, but I'm just going to show you a toy example. So here's a toy example and a little bit of light math. Okay, so here's an example of something we may want to do and generate training data. And there's a whole longer talk here of how exactly this works. Let's say you want to do named entity recognition. You want to label persons and hospitals in text. Okay, you just want to know, you have some mentions. Are these mentions of people or text? St. Francis could be a person, could be the hospital. Bob Jones, probably a person, but I guess could be a hospital too. Okay, so here's how these weak supervision frameworks work. They basically allow you to have these little voters that you write to reuse training data that you had before. An existing classifier that's already voting person, you just throw it in. Here's another kind of classification rule. Uppercase existing classifier says person, you put that in. And then hospital, well, I have a dictionary of hospital names. It's called distant supervision. So this one votes hospital. And the point is each one of those noisy sources in the sewer is telling you something different. And all you want to do is determine how likely is answer A versus answer B. Okay? So this is how it works in a particular engine. This is the first system that did it. There's many others since then. Don't worry too much about that. But what it did is it estimated this graphical model. And I'll show you how it works in just one second, because it will look very familiar to you. You take in all those sources and you try to estimate how accurate is every source and how correlated is every source with one another. And then you make an estimate over all the labels for every point. How probable, how likely is it as a person, a hospital, or whatever? Okay? That's what you want to do. So we model this as a generative process. Okay? There's the graphical model there. You've probably seen something like this. And the instance here is we want to learn the Y value that's there, the label that's there, without any hand-labeled data. So we want to look at the votes and somehow deduce the Y. Okay? There are reasons you want to do this that are beyond this, but we're not going to have any labeled data when we do it, and we want to learn the correlations and the accuracies. Okay, awesome. So it's not at all obvious that you could do this. The reason it works is because you can see these voters on many data sources, millions of data points. Every point that comes in, every voter registers, yes, no, or indifferent. And you can look at their overlapping judgments and estimate their accuracy and their correlation. If you knew, for example, source 1 was always right, you just count how often every source agreed with source 1, and that would tell you the accuracy of source 2 and source 3. Okay? But they could be correlated, as we saw. That first function and second function called each other. They could be correlated in some way, and you'll have to deduce that. Okay? All right. So here's the way that you solve these underlying problems. I'm just going to go through this very quickly because we don't have all the math, but it basically looks like those covariance matrices that we saw from before. The problem here is that we want what's in the red. We want to know how often does Y, which we don't see, how often this thing, let's make it 0 or 1 so it's true. We don't see how often Y is correlated with one source. We only see how often the sources are correlated with one another. So said another way, we can only observe what's in sigma sub O. We don't get to see how often the sources correlate with the ground truth. Okay? Now here's the thing that is pretty interesting. It turns out that the inverse of this matrix has a structure. This is one of the most beautiful mathematical facts that comes from the graphical models course, and I'll just state it here without proof. It turns out that every time this graphical structure is missing an edge, there's a 0 in the covariance matrix. Okay? This allows us to write this in terms of the observed values and some rank 1 parameters. And these ZIs basically say if they're 1, they have perfect accuracy, and 0, they're total noise. Okay? Now why that's interesting is it lets us set up a bunch of these equations that basically say we know the left-hand side is 0, because let's imagine I know the structure, I know how they're correlated. You can solve for that if you wanted. And it turns out, this will be kind of weird stuff, it turns out that actually here, you can complete this as long as you have enough of these linear constraints. Now, a couple of things here. First, z and minus z are solutions. So this gets us back to those symmetry questions I wanted to highlight. You can't tell if everybody's correlated with the ground truth or the exact opposite. You have to make an assumption. If you had a bunch of malicious labelers who were all telling you the exact wrong thing and correlated to each other, you would get fooled. So you have to make some assumption there. The second thing is when zi is equal to 0, that means it's a coin flip. If I added a labeler that just flipped a coin, this should give you no information. And indeed it won't. It will zero out every constraint that it's in, which sanity checks. You can't kind of make your job easier by adding these labelers. It turns out, I won't bore you, there's a great paper from Vershinin from like 2014, 2015 that measures the notion of rank in a continuous way. It's called effective rank. And this tells you the right statistical scaling for this problem. The closer those z's get to 0, when can you recover the matrix? It's super fun stuff. It's a nice geometric piece. Okay? So you heard all this stuff. I just wanted to share it with you. It's stuff that I end up working on. You probably think at this point, like, there's no way anyone would ever use these crazy covariance matrices. But I just want to share one thing with you, which is wild to me, because my students did this. It's actually used in all these applications. It's still in production all these years later. And this is a way that people cope with the fact that they have lots of noisy training data and put them together. So it's in search ads, it's in YouTube, Gmail, and products from Apple. And so this weird framework of how you program training data, just something I wanted to share with you. And the underlying model is like classical from what you've seen, except for instead of solving these EM problems, you solve these weird covariance matrix inverse problems, and you can solve them provably. And that turns out to be important for a variety of weird issues of like estimating source quality. You don't want to rely on EM, which we talked about doesn't have a unique answer. For this, we can tell you exactly where the unique answer is. Thank you for your time and attention, and Tengyu will see you on Wednesday.